we are going to prove our proposed chain rule. We have decided that we think the chain rule should be the derivative of f of g of x is f prime of g of x times g prime of x. And I want to go back to our limit definition to prove it. And I think this one is really cool. Someone had to get very clever to get there. And I don't know that I would have spotted this without knowing in advance what I think the chain rule should be. So to set up our limit definition, we have to realize that our function in this case is f of g of x. So we need to take the limit as h goes to 0 of f of g of x plus h minus f of g of x all over h. So that's our usual difference quotient setup. And I'm going to start by doing something that really looks like it's just making this a whole lot messier. I'm going to multiply by g of x plus h minus g of x all over g of x plus h minus g of x. So I'm multiplying by 1, but I've made my 1 look like this whole mess. And my thinking here, where this would come from, is if we know this is what we think the chain rule should be, we want to find a g prime out at the end. So we're basically introducing pieces of g prime. The next step I'm going to do is really just a quick rearrange. I'm going to switch the denominators of the fractions. So we'll have that same numerator, but this is now going to be over g of x plus h minus g of x. And then we're multiplying by the g of x plus h minus g of x all over h. So these are definitely still equal. If you doubted at all, remember to multiply fractions, you just multiply straight across. So we'd get this whole f of g mess multiplied by the whole g of x plus h minus g of x mess. And then on the bottom, we'd have h times the g stuff. Down here, we'd have the same thing, exact same numerator. The denominator is just written in a different order when we multiply, but it is equivalent. So now I've got my g prime of x that I think I should get. Again, I don't know who came up with this the first time. I don't know that I would have ever come up with this without knowing I'm looking for a g prime of x, but I think it's pretty cool that somebody did. So looking at this f of g of x plus h, I really need to work on improving this a little bit. I'd like to find an f prime in that mess. I'm going to try and hide some of the g pieces. So I'm going to start by replacing g of x with a w. And I also want to hide that really messy denominator. So I'm going to replace g of x plus h minus g of x with a k. And I really also want this g of x plus h piece right here to go away. I want to hide all the g of x pieces. I've just not called that one out in the same way because I don't need to define another variable. I've already got it covered if I just work with what I've defined here. If I continue with this, I can say that k is equal to g of x plus h minus w, which means that w plus k is equal to g of x plus h. So that will replace that final piece. So I'm down to the limit as h approaches 0 of f of w plus k minus f of w all over k. And then this is times g prime of x. And I want to notice one more thing. If I go back up to where I defined k, right here, notice that as h goes to 0, this entire expression also goes to 0. So k goes to 0. And all I'm saying there is if this number becomes infinitely small, you basically have g of x minus g of x, which is 0. So really in this limit I wrote, saying h goes to 0 is the same as saying k goes to 0. Both will happen. If one happens, the other happens. And if I'm letting k go to 0, then really this becomes f prime of w. I know the variables are a little funny, but that is difference quotient with variable w, and then the distance between 2 points is the k, which is going to 0. So I have f prime of w times g prime of x, and then remember, w is just something I threw in here. W represented g of x, so this is f prime of g of x times g prime of x, and that's what we were hoping to see. So back to my claim at the top, this is true. Again, this is your chain rule. Memorize this. This tells you how to deal with the situation where you've plugged one function into another function. You always take the derivative of the outer, leave the inside alone, and then you multiply by the derivative of the inner.